Okay, in this ShowMe, I'm going to introduce you to the basic terminology of polynomials. We're going to talk about how to add and subtract polynomials, and we're also going to address the standard form of polynomials. So there'll be a lot of little housekeeping items here, and then a couple of very important examples at the end. Before we get to polynomials, we need to know about the building blocks of polynomials. All polynomials are sums of monomials, and all a monomial is a term in a polynomial. Now, a lot of times, polynomials don't have to have more than one term. For example, here is a monomial. It's also a polynomial, but it's only one term. Here's another. One of the things you have to watch for with all polynomials, however, is that the exponents on the x's, or whatever variable happens to be in the term, those exponents have to be whole numbers. That means they can be 0, which means they won't appear. They can be 1, 2, 3, and on. They cannot be negative. If you see a negative exponent, you're not dealing with a monomial or a polynomial. So again, a monomial is simply a term in a polynomial. Of course, some polynomials only have one term, so those are monomials as well. But one of the big things to watch out for in everything we do in dealing with polynomials, the exponents have to be whole numbers. That's 0, 1, 2, 3, etc. And anytime you see a constant in a polynomial, that just means that the exponent on that variable happens to be 0. There's one more term we have to deal with before we get to polynomials, and that is the idea of degree. Degree refers to the exponent on the variable in a given monomial. So, if a monomial looks like this, now that really is a monomial, it actually means that you have 6 times your variable to the 0 power. That term, its value will never change regardless of what x is, as long as x isn't 0, of course, because anything to the 0 power is 1. That's always going to be 6. So those are constants. They don't change. They're the same forever. If you have a monomial like this one, we call that a linear monomial. Its degree is actually 1 because the exponent on the variable is 1. So first-degree monomials, first-degree polynomials, are linear. We've been dealing with linear polynomials for quite some time. We've been dealing with them every time we've worked with straight lines. Thus, the word linear to describe first-degree polynomials. Second-degree polynomials, like this one, are called quadratic. They're given that strange name because they have long been associated, or were long associated, with the futile search for a way to square a circle with a compass and straight edge. In other words, to create a square of equal area to a circle with a compass and straight edge. It can't be done because pi is irrational. Anyway, that's why we call them quadratic. After that, the names start to make a little more sense to us. Third-degree terms are called cubic. Their association with the cube being the obvious reason. At fourth degree, they call them quartic, although you don't really need to know that for an Algebra 1 class. And fifth degree, they call them quintic. We're not going to really deal too much with those. Our focus is mostly going to be on polynomials of degree 0, 1, and 2. Because that's where we learn the basic techniques that we can then apply to the larger degree polynomials in later and more advanced classes. Anyway, the idea of degree is very important, as you'll see in a little bit. But remember, some of these things, when you hear certain words, that implies a certain degree, even though you won't hear the number. If someone says that something is constant, that has a degree of 0. If something is linear, that has a degree of 1, and you'd expect the leading variable term in any expression representing it to only have an exponent of 1. If you hear quadratic, that means that the leading exponent will be 2. Cubic, 3, and so on. As I said, these words down here are a little more arcane, but the real point of all this is that there's a language that surrounds these numbers, and all of it surrounds the idea of degree, and different polynomials of different degrees have certain characteristics. These are real classes of polynomials, and they have certain properties and certain habits in the way that their graphs look and the way that we work with them that you'll need to know. Now finally we're ready for the big word for this next unit that we're starting today, polynomials. A polynomial is a sum of monomials, and monomials are just what I've been showing you. They are products of a constant and a whole number power of a given variable. Could be more than one variable, although for the work that you'll do in an introductory algebra course like the ones that I teach, for the most part you won't be seeing two variable expressions very often. All polynomials are a basic form that looks like this. We have some constant, a coefficient, being multiplied by a whole number power of a variable. In this case we'll say x. Then it's added to another one. Now we pair the coefficients with each term, so I'm going to count down from n to 0 throughout this sum. At the same time the powers are going to go down from n to 0. So then n minus 1 is the next power, and then n minus 2 as we keep going down to 0, which will be the last term in the polynomial. I haven't specified just how many terms there will be in this particular polynomial, but at the end the process still continues. We'll have a quadratic term, we'll have a linear term, and we'll have a constant term. And remember, in that very last term you won't see that x. It'll be x to the 0 power, which is 1. And this is a general form of a polynomial. How will it look in real life? Well, it might look like this. Negative 3x cubed plus 4x minus 5. That's a cubic polynomial. It has 3 terms. Notice it's cubic because its leading term has a power of 3 associated with it. Only that leading term decides the degree of the whole thing. This entire polynomial is a cubic polynomial. Yes, it is a sum of a cubic term and a linear term and a constant term. That's all true. But the character of the polynomial is defined first and foremost and mostly by the term with the greatest power of the variable in question. In naming polynomials according to the number of terms they have, we count using the first 3 numbers from our Greek prefixes. So mono is the Greek prefix for 1. A single-termed polynomial is a monomial. The Greek prefix for 2 is bi, as in bicycle. That's called a binomial when you have a polynomial with 2 terms. And of course, if it has 3 terms, it's called a trinomial. If it goes beyond 3 terms, we just call it a polynomial. Poly is not the Greek prefix for 4. That would be tetra. But once you get past 3, we just don't bother counting any higher in Greek than that. So when you name a polynomial, we now know 2 ways to do it. First of all, we could name it by its degree, and we can also name it by the number of terms. And in fact, that's what we're going to do. You'll have practice exercises undoubtedly in your textbook or from your teacher, where you'll have to name polynomials according to both degree and number of terms. In most courses like this one, the heavy focus, the overwhelming focus of our work with polynomials for the whole first chapter, or a unit in which you work with them, is going to be quadratic trinomials. We're going to spend an inordinate amount of time with those, particularly learning how to decompose them or factor them into linear binomials. And that's going to be a crucial skill, one of the most important and most challenging skills of the elementary algebra student. Once you've mastered that, you've made a huge transition in the way that you think and understand algebraic expressions. And that's one of the reasons, it's one of the core topics that makes Algebra 1 such an important gateway course. Let's return to that initial example I gave you of a polynomial of n degree and of unknown number of terms. Actually, it would have n plus 1 terms, but that's not the point. The point is, standard form of a polynomial is an essential idea. It's very important when you work with polynomials that anybody with whom you communicate about your work can quickly see what the degree of the polynomial is. For that reason, we always put the term that has the greatest degree first. So if someone gives you an expression like this, 3x squared minus 7x to the 5th plus 2x minus 1, that's not an appropriate way to convey the information. And whenever you work with something like this, it's incumbent on you to turn it into a standard form expression. If you looked at this expression and didn't look at it carefully enough, you might think it was quadratic, but it's not. Yes, the first term is quadratic, it has a degree of 2, but actually this is a quintic polynomial because the term with the highest degree has an exponent of 5 on the variable. This is supposed to be written negative 7x to the 5th plus 3x squared plus 2x minus 1. Now the important information is right there in front where it belongs. And it is expected of you, and I got to believe most teachers are going to take some points off, it's always expected of you that you will deliver your answers regarding polynomials in standard form. You need to learn that convention. That's one of those important little math club conventions that you need to know so that when you move on to more advanced courses, two things happen. First of all, you fit in with the other students and with the teacher. And second of all, you don't embarrass your poor math teachers. Folks like me count on our reputations. We don't have much else sometimes. Okay, now several examples to get you started. This is an example in which you are expected to rewrite the polynomial in standard form. As I just told you, standard form means that the term with the greatest degree is listed first in every case. That translates all the way down the line. Every term should be the highest one that's left when it's written. So the highest term left at this point is negative 10x to the 5th. Now that it's been written, what's next? 5x cubed, and we don't see it, but there's a plus in front of that 5. And finally, only one term is left, and that's 8. So this is the appropriate way to write the polynomial that we started with in standard form. Another example just like it needs to be rewritten with the greatest degree terms leading off. The first term that should appear is negative 2, y to the 4th. Then we should have plus 4y squared. And finally, minus 3. Remember, all of your answers about polynomials, all the sums and differences and products and factors that you create should always be written in standard form with the term of the greatest degree appearing first. I'm glad to report that adding polynomials is a very simple process if you remember your lessons about combining like terms. When you have two addends like these, delineated by the parentheses, you simply match up the terms that have the same degree and make sure that you only add those together. And remember that terms that don't have the same degree can't be added together. So to get this sum, you can add 11m squared and 7m squared to get 18m squared, and then 5 and 6 to get 11. Now that works great for this situation. Before we get to something too complex, let me show you a great way to write these that makes it even simpler. You can write 11m squared plus 5 and then 7m squared plus 6 in a vertical fashion, just like we used to do with addition back in elementary school, and then add straight across. 11m squared plus 7m squared is 18m squared, and 5 plus 6 is 11. No need to worry about carrying or borrowing in this situation. This is not a true place value situation. Notice that in either case, the answer was 18m squared plus 11. It doesn't matter so much which one you use for a problem like this one, but as you'll see in some of the more complicated examples, it may make a difference. This problem is done pretty much the same way as the one we just did. Important to remember, however, some things about coefficients. When you see negative t squared, as you do at the beginning of this first addend, remember that there's a number there. And if you don't see it, it's going to be a 1. So negative 1 t squared is really what leads off that first addend. Now when we combine like terms, we have negative 1t squared plus 2t squared, which is 1t squared. And you don't have to write that one in your answer, but you can if it helps you. Then for the rest of it, negative 7 plus 12 is 5, and that'll be a plus 5 because it's positive. Here's another place where perhaps organizing things vertically will work better for you. T squared minus 7, and it was negative to begin with, and then 2t squared plus 12. It's important to remember that you are adding everything, even though you see all these minus signs. So what's really going on? Well, you are adding a negative 1 here, and you're adding a negative 7 here. Now, I've got a colleague who insists that all of his students do that. It doesn't harm them any, and if you want to use that method, I think it'll help you. But I don't require it of my students either, and I don't really do it myself. Anyway, to finish the process, negative 1t squared plus 2t squared is still t squared. Negative 7 plus 12 is 5. In my class, at least, if you write the coefficient of 1, I'm not going to mark it wrong, but it does not have to be written, and be aware that there probably will be a teacher or two in your future who expects you to write everything as simply as possible, and extra marks are at least annoying, possibly worth a -1 somewhere along the line on a test problem. Now we start encountering some of the little tricks that book authors and test makers can play with you. This problem here requires us once again to use our like terms skills. So make sure you're matching up terms that have the same degree. 10w cubed matches up nicely with 8w cubed. 7w squared, however, doesn't match with anything in the other polynomial. And that's okay. Don't let that bother you. Don't insist on adding things if they don't go together. But notice that 3 doesn't match up with anything in the original addend either. So actually, even though we're adding two addends that have 2 terms each, we're going to get a sum that has 3 terms because we're going to generate 3 unlike terms. That's all right. Don't let that throw you off. 10w cubed plus 8w cubed is 18w cubed. That's the one part of this that's going to feel normal. 7w squared can't be added to anything, so it moves on to the sum intact. And the same thing happens with 3. Don't get overly enthusiastic about the adding thing to the point that you incorrect yourself, that you take what is going to be correct work and make it wrong by trying to overcook it. This is a place where the vertical arrangement can really help you if you adopt one particular rule for yourself. And that rule is, if a degree in the sequence from the first term to the last term is interrupted by a lack of a term, you have to put a 0 in as a placeholder. Let me show you what I mean. If we were to organize this problem vertically, you'd write 10w cubed plus 7w squared, no trouble there. Now what's missing? Well, there's no linear term, there's no constant term. Put a linear term in, put in a constant term. Just don't put in anything that's going to change the actual value of what you're talking about. 0w plus 0 doesn't change anything, but it cleans up the mess that could exist if you don't put them in. Now put your other addend in. 8w cubed, right under 10w cubed, but 3 is a constant. It belongs over here with the constants. What about the missing quadratic term? What about the missing linear term? Well, put them in. Don't let that bother you. Now everything is fine. Now it all makes sense. And now you can add. 10w cubed plus 8w cubed is still 18w cubed. 7w squared plus 0w squared is 7w squared. 0w plus 0w is 0w. We don't need to write that. Don't write it. Just leave a space, that's okay. And then 0 plus 3 is plus 3. Just remember to make sure that your instructor or whoever's evaluating your work can see that all of these terms go together. In this fashion, you can avoid silly mistakes that come from being a little overzealous in your addition. A lot of students get excited. This is something that doesn't seem that hard, even though we have all these new words floating around. And they get a little too excited about it and actually end up making more mistakes than they should. Don't let that happen to you. Be careful. Be meticulous in your organization. Take a little longer to make sure that you get it right. It's worth it. Now here's an area where there's going to be some confusion. You're going to make a mistake or two at first. When it comes time to do subtraction, I really recommend strongly that you don't use the like terms approach. Can it be done? Sure it can. Here's how it would be done if you're going to insist on it. 2x cubed goes with 8x cubed. Of course, we're subtracting now. So it's not 2x cubed plus 8x cubed. It's 2x cubed minus 8x cubed. And 2x cubed minus 8x cubed is negative 6x cubed. Then we have 5x squared minus negative 8x squared. Okay, 5 minus negative 8 is positive 13. So you're going to have 13x squared there. And then negative 2x minus positive 4x is negative 6x. That works, but I find it unreliable and dangerous to work across a single line with all this information. I really strongly recommend that you use vertical organization for your subtraction problems involving polynomials. And that means writing the problem out like this. Just writing the two terms out. And then I really recommend that you employ the definition of subtraction. Subtraction is adding the opposite of the subtrahend. The second number becomes the opposite of what it was, and then you simply add. It's a much more reliable way to do things than to try to remember across the board that you're subtracting. So, everything on this second line is going to become the opposite of what it was. Positive 8x cubed becomes negative 8x cubed. Negative 8x squared becomes positive 8x squared. And positive 4x becomes negative 4x. Now, add. 2x cubed plus negative 8x cubed, negative 6x cubed. 5x squared plus 8x squared, positive 13x squared. Negative 2x minus 4x, negative 6x. That, in my opinion, is the safest way to get yourself to the right answer reliably when you are subtracting polynomials. One last word on subtracting polynomials. Adding them as well, this can always happen, that a term will drop out and just simply disappear from the problem. That happens, it's okay. Don't freak out when it happens. Here's a subtraction problem. I recommend that you organize it vertically. Let's write all the terms out just as they are in the original problem. And then take the second row and make those all the opposite of what they used to be. Now add. 5x squared plus negative 5x squared is 0. It's gone. That's okay. 4x plus negative 2x is 2x. 2 plus negative 7 is negative 5. And that's okay. That will happen. Don't let that bother you. You don't need to put a 0 in for what's missing, although if you want to, I suppose that's okay. When it comes to adding and subtracting polynomials, eventually it will be as easy as it looks. Unfortunately, if you're not good at managing details, if you're not meticulous, it won't seem so easy for a while. So please take your time. Don't just take it for granted this is easy. When you do that, you set yourself up to make a lot of silly mistakes. There may be little flaws in your organizational process, even in your addition and subtraction skill, that you can only remediate by being careful. So please, be careful. Dealing with polynomials is all about the details. If you can manage the details, if you can stay organized and be meticulous, and not rush through all of your work, you should be fine with the entire unit.